Now that we know how sequences work, we want to think about the limits of a sequence. So suppose that f is a function such that f of n, where n is positive integers, is equal to a sub n. In other words, f of x is that curve, that continuous curve, right? But f of n is a sub n is only those specific dots along that curve, those specific points. If the limit as x goes to infinity of f of x is L, then the limit of the sequence a sub n is also L, where L may be positive or negative infinity. This could work for infinity as well. So think about what this is saying. It's saying that, hey, if your function is going to a specific value, so you have your L right here, and if your function is going to that value, here's your value, here's that horizontal asymptote, and that black curve is approaching that, then the sequence will also approach it because the sequence is built from that black curve. I mean, it just kind of makes sense, right? So if the function is going to a curve, then the dots along the function are also going, if the curve is going to that line, then so will the dots that are specific points on that curve. They will also go to that line. Now, the function, of course, is continuous, right? Right here. So it's the continuous black curve, continuous. But the sequence that's built from pieces of it is discrete. There we go. I can spell it's a C, but it doesn't look like a C. There we go. All right. So since the limit of the function is L, then so is the limit as n goes to infinity of a sub n. Sorry. All right. Now, the converse is not true. All right. So I love it when they put these in books and then they kind of expect you to know logic theory, So converse, what's that? Well, let's go back here. All right. So this statement says if this, then this, right? So if A, right, this being A, right, there's A, then B. If A is true, then B is true, right? The converse says that if B, then A. If you ever take a theoretical logic class or philosophy class, they'll talk about this, or math classes. We talk about it a lot of time in math classes. So the converse is if B, then A. All right, well, that's not true, right? So if B, then A is not true. So just because the sequence has a limit does not mean the function has a limit. And that's what they're showing us right here. So if you look at these values, right, a sub n is the cosine of 2 pi n. So all the values are 1. So the limit, oh, I wrote it right here, of a sub n, the limit of the sequence is 1 because every little dot on that sequence is 1. So it's 1, 1, 1, 1, 1, 1, 1, no problem. But the curve, the function, the continuous curve, right? So that was true for the discrete part. But for the continuous part, that's not true. Right? And that's what they're saying. The converse is not true. So we learn up above that if the function's going to a value, then the sequence has to go to a value. But if a sequence goes to a value, that does not mean the function has to. This particular one is an oscillating function that actually never goes anywhere in particular. So it's an oscillating function. You can see it. It's doop-de-doop. Cosine and sine are oscillating functions. All right, so now going back to if the function goes to a value, then the sequence that's built from that function goes to a value. Let's think about what are some possibilities for n behavior of a sequence. All right, now the sequence could converge. We love it when it does. Convergence is great. makes us very happy because we get a number for an answer. So it's thrilling. So for example, on this one right here, I can see it seems to be going to a half. So the limit as n goes to infinity of a sub n seems to be a half on this one. Right? And then over here on this one, well, it looks like the limit is 0. It's oscillating, right? It's bouncing up and down, right? Positive, negative, positive, negative, positive, negative, positive, negative. However, it definitely appears like it's going somewhere. So the limit, it looks like it's going closer and closer and closer to 0. So the limit as n goes to infinity, I'll call this one b sub n, is 0. These are converging. It's converging to a value, right? A single value like a half or 0 or whatever, right? So as n goes to infinity, right, which means you're moving right on the sequence, move right on the graph, right? Literally, move to the right, right? So as we go to the right on the graph, the points are approaching a horizontal asymptote, which you can see is what I'm drawing right there. All right, we love when this happens, right? Convergence is wonderful. Makes us very happy. And then there are multiple types of divergence. So this one makes us thrilled. These ones, not so much. All right, so there's divergence in terms of infinity. So this particular one, you can see that it's shooting off to infinity and beyond. Sorry, I have to say the Buzz Lightyear thing. All right, so this is the limit as n goes to infinity of, I'll call this one Cn, is infinity, right? It's shooting up, 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 right? It's just going to keep growing and growing and growing. That's divergence, right? It's increasing in magnitude without bound, right? So it's going to either infinity or negative infinity, right? So this is saying the limit as n goes to infinity is, as n goes to infinity of c sub n is either infinity, negative infinity, or both, right? You can have a mixed sign, which actually means it doesn't exist, oscillating, which is this one right here, right? So I guess I should just say does not exist. Let me just do it that way. But it's increasing without bound, so it's oscillating plus or minus infinity. Let's say it that way, which means it does not exist. All right, so that's this example over here. As a matter of fact, I'll make it a little bit darker so you can see. So the one over on the right is oscillating between plus or minus infinity, right? It's growing larger and larger and larger. Positive infinity, negative infinity. That's what's happening. So it's oscillating between plus and minus infinity. Therefore, the limit of this particular function does not exist. Or sorry, this particular sequence does not exist. Right? So that one's a does not exist. This one's an infinity. Technically, this one is positive and negative infinity simultaneously, which means it doesn't exist, right? So it's bouncing, and it just keeps bouncing between the two. So it's growing larger and larger and larger. So that's when it says mixed signs. That's an example of this one, right? Because it's bouncing positive and negative, positive and negative. It occurs to me I forgot to box the answers here, right? So half and 0. Now, it can remain bounded, but settle into an oscillating pattern which the terms approach 2 or more values, in which the case, all right. So what it's saying is it's oscillating between 2 values or more values. Sometimes it could be 3, but it's just bouncy, 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 but it's never going to get anywhere, right? So both of these, for both E and F, I'll call these, neither one of them has a limit that exists, right? Because it's bouncing between 2 numbers. So the limit as n goes to infinity of E sub n and the limit, right? And same with this one, right? Neither one of them exists. The limit as n goes to infinity of F sub n does not exist. It's just bouncing, 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 right? Up and down and up and down and up and down. It's never approaching a particular number. And then there's one more that's really wild. It's bounded, right? It never gets higher or lower than these values. That's what bounded means, right? It's hemmed in, it's bounded. So it never gets above this line, it never gets below that line. However, it's just chaos in between. It's just going all around and doing crazy things. So as I move right, it has no particular pattern. It's not heading anywhere in particular, right? So all of these are divergence. There's divergence to infinity. There's divergence to plus or minus infinity. You could also have divergence to negative infinity. You can have divergence in terms of just bouncing between two numbers. And you can either bounce all the time or you can bounce later on when you kind of have grown into it. Or you can just bounce chaos, right? So just wandering around chaotically between two boundary lines, right? They're just random dots in there. And therefore, the limit of this sequence also does not exist. I'll call it G sub n when in alphabetical order. All right, now putting it all together, let's find some limits of sequences. Okay, so I have this sequence here, which is a sub n is n cubed minus 2n cubed. Okay, so I can use the rule that I already know, or I could use L'Hopital's rule, right? And I can prove, right, since the degree of the numerator is equal to the degree of the denominator, then the limit will be equal to the ratio of the leading coefficients. So, using table, in our case, this semester, it's on page 198. If you're watching in a later semester, that page number might change, but there you have it. So using the table on page 198, I know that this would be equal to 1 over negative 2. Oh, sorry, the limit. The limit as n goes to infinity of a sub n is 1 over negative 2. Now, if you want to do it with L'Hopital's rule, you can. You would just take multiple derivatives. It would take you a few steps to get there. They're not hard, right? All right, now what about the next one? Oh, okay. Well, this one, maybe let's try with L'Hopital's rule, because the table does not apply, because the table is, again, for rational functions. And that denominator we have is not rational, or is not a polynomial. So it's not a polynomial, so it's not a rational function. So we will actually have to show this one. Cannot use the little trick. The page 198 table, right? We cannot use it. Okay, so the limit as n goes to infinity of n squared over 2 to the n minus 1. Luckily for us, that's infinity over infinity, right? Infinity squared over 2 to the infinity power is infinity over infinity. So I will use L'Hopital's rule, and I will take the limit as n goes to infinity of 2n over the derivative of 2 to the n is natural log of 2 times 2 to the n. The derivative of 1 is 0. Well, that's still infinity over infinity. So I'm going to take another L'Hopital's rule. And then it's the limit as n goes to infinity of 2. And then I have a natural log of 2 there, but I'm going to get another one from taking the derivative. So it's natural log of 2 squared times 2 to the n. And that's 2 over infinity, right? It's technically 2 to the infinity power, but that's 2 over infinity, which is 0. All right, next one. Oh, our favorite. We love it when it's like this. All right, again, cannot use, right? This is not rational, cannot use that table. So we'll have to do this longhand. All right, so we'll let L equal the limit as n goes to infinity of n to the 1 over n. And you're thinking, that sounds familiar. Yes, it's because we've done it before. All right, then we'll take the natural log of both sides. So we'll get the natural log of L equals the limit as n goes to infinity. And you take the natural log so you can bring 1 over n down in front. Okay, so that's equal to the limit as n goes to infinity of the natural log of n over n. That's infinity over infinity, right? Technically, it was right here too, but I didn't know if it was as obvious. So let's use a L'Hopital's rule. So put a little apostrophe, L apostrophe H, and then we'll take the derivative. So this is the limit as n goes to infinity of the natural log of n's derivative is 1 over n divided by 1. So then I can put infinity in. It's 1 over infinity, which is 0. But remember, this isn't the answer. This was the natural log of the answer. So L, which is what I really wanted, is e to the natural log of L, which is e to the 0, which is 1. And last but not least, there's some basic properties that just sort of make sense. The limit laws for sequences. So if you take the limit of each individual sequence, then you can just add up the limit of this one sequence plus the limit of the other sequence. And same with subtraction. Assuming, of course, that they are convergent, right? That's kind of, it's assuming convergence, right? They're assuming that they converge to a number, each of them, right? A sub n goes to A, B sub n goes to B. Therefore, you can just add and subtract those limits. If you multiply by a constant, right, C being any real number, then you could just multiply by C and you'll be fine. You can multiply and you can divide those limits, provided, of course, that the denominator is not 0, because the denominator being 0 is always not good for us.